In this video, we are going to talk about probability. This is the introduction video of probability. We'll only cover the basic concepts. Okay. So let's first start with the sample space. Sample space is the set of all possible outcomes related to a random experiment. Random experiment. Please focus on the phrase random experiment. Random experiment means you know all the outcomes, all the possible outcomes of the experiment, but you do not know the result or the outcome of the particular trial or the experiment. For example, you roll a dice, you know all the possible outcomes, that is 1, 2, 3, 4, 5, and 6. But when you roll a dice, you do not know which number will appear on the dice. Okay, so that's the random experiment. And sample space is denoted by the capital letter S because this is a set. Okay, and we also use the another notation, that is ohm. This is ohm. So for dice, the sample space would be 1, 2, 3, 4, 5, and 6. Similarly, when you toss a coin, the sample space would be head and tail because these two are the possible outcomes. All right. Now, before we learn about the probability, we need to understand a few words, few terms. So let's go through them one by one. So first word is event. Now people often get confused with between event and outcome. These two are the different thing. Outcome is simply the result or the output of the experiment. Now event is the subset of a sample space. So any subset of a sample space. So outcome, like when you roll a dice, you get either 1, 2, or 3, 4, 5, or 6, right? So those are outcomes. But you can define an event, for example. Now this is also a set, that's why I'm using the capital letter A. So suppose you define event A, getting even number on dice, even numbers on dice. Okay, so we write event A as the set 2, 4, 6 because these are the possible outcomes, right? These are the possible even numbers that can appear on the dice. Okay, so this is the event, and the event can also be the sample space, or sample space can be the event. Okay, so for example, you can also say event as the numbers appear on the dice. So those number can be 4, 5, and 6. Let me use the different notation B. Okay, so event is the subset of the sample space, and an empty set can also be the event. Okay, so suppose for example, you want to get 7 number on the dice. Is it possible? No, right? Because there are only 6 possible outcomes from 1 to 6. So you cannot get 7 number on dice. That is an impossible event. Okay, so that's the null set, empty set. Now, what is the probability of event? So probability of event, let's say E, is simply the number of favorable outcomes divided by the total number of outcomes. This is sample space. We can write this as n of E upon n of S. So this is the number of favorable outcomes in the numerator, and in the denominator we have the number of outcomes, all possible outcomes. Now the range of probability is less than or equal to 1 and greater than or equal to 0. For example, the probability of an individual, dying at some point in the time, at some point in the future, is 1, right? Because it is for sure that the person will die either at age 50, 60 or 70 or any other age. Okay, so in that case the probability will be 1. All right, so the probability ranges between 0 and 1. Now let's look at few laws of probability. So first law is probability of sample space is 1, and you can see this from the formula as well. In the numerator, if you put the sample space as the event, then this becomes, you can cancel this out, right? So this is simply 1. Similarly, probability of impossible event is 0, the event that cannot occur in any circumstances. That's why the probability is 0. Now probability of complement of an event is 1 minus probability of that event. And you can also look at this from the diagram, Venn diagram. So suppose this is your sample space and this circle is A, the event A. So what is A complement? So A complement is the area outside this circle, right? And the area of the sample space is always 1. So you can subtract this circle from 1 and you will get the A complement. You can also understand the probability in terms of area. Okay, so we are basically calculating the area, and that area is the probability. So in this case, the area outside the circle is A complement, and that area is the probability. Because the total area is 1, so the area minus 1 will always be in the range of 0 to 1, right? So this is the probability. Now, what is the probability of A union B? We can also read this as A or B. So this is probability of A plus probability of B minus probability of A intersection B. Let me show you from the Venn diagram. This is our sample space. This is event A and this is event B. Now you can see that there is a overlapping region. There is an overlapping region, this region. So A union B is the total area, okay, including the overlapping region. So when you add A and B, you are double counting this overlapping region, okay? So you need to subtract once and then you will get the A union B, okay? Now you can also derive the formula for probability of A intersection B by making it the subject. So probability of A intersection B is probability of A plus probability of B minus probability of A intersect union B, okay? Now, apart from this, we have two very important laws which we call De Morgan's laws. So let's look at these. So the first De Morgan's law is probability of A union B whole complement is probability of A complement intersection B complement. And the second law is probability of A intersection B whole complement is probability of A complement union B complement. So this is De Morgan's law. There is a trick to remember this law. Break the line and change the sign. Change the sign. Like for example, in the first law, you can see that the this longer line is broken into two parts. Okay. And then union is changed into intersection. Okay. And similarly, in the second formula, the longer line is broken, and then intersection is changed into union. So this is how you can remember. This is basically a trick. So you can remember this two laws. You can frequently use these to calculate the probability. Now let's look at the mutually exclusive events. Mutually exclusive events. So as name suggests, exclusive means one event will exclude the possibility of the other event, right? So suppose this is your sample space and this is the event A and this is the event B. There cannot be the overlapping region. Okay, one event will exclude the possibility of the other event. In this case, probability of A intersection B will be 0. You can also consider this as the disjoint set. Disjoint set. There is no common in sets. Okay. In this case, probability of A union B is simply probability of A plus probability of B, the sum of the individual probabilities. Now, the example of mutually exclusive events could be, for example, the event A is getting king from the 52 cards and event B is getting ace from the cards. Now these two events cannot occur at the same time. I mean, you cannot get king as well as ace in the same card, right? This is not possible. If you have ever played cards, then you know that the king and ace cannot appear in the same card. That's why event A and B are mutually exclusive. So these two are mutually exclusive. Either you can get king or ace. All right. Now there is one more term, that is mutually exclusive and exhaustive. Mutually exclusive and exhaustive events. So exhaustive means the options or the possibilities will make up the sample space, or the events, the total events will make up the sample space. So let's look at from the diagram. So this is the event A and this is B. These two are the exclusive, right? Either A will occur or B will occur. There is nothing common in these two events. Okay. And these two events make up the sample space. This this rectangle is the sample space, right? And the area of A and B make up the sample space. Okay, so that's why A and B are mutually exclusive as well as exhaustive events. So the probability of A union B in this case is simply 1, because these two events make up the sample space. Now, the example of mutually exclusive and exhaustive events could be, suppose you take an exam. So there are two possibilities that can happen. Either you can pass or you can fail, right? There is nothing in between. You cannot pass as well as fail at the same time. This cannot happen, right? So passing and failing are the mutually exclusive as well as exhaustive events. These two events make up the sample space, and these two are the exclusive events. Okay, so this is one of the examples of this kind. Now let's look at the conditional probability. Conditional probability. We write this as probability of A given B. Okay, so this is, we can read this as probability of A given B has already occurred. Okay, so B has already happened. Now what is the probability of A? So we have a formula, probability of A intersection B divided by the probability of B. We use the conditional probability in in very specific circumstances. For example, let me give you one real life example. Like in insurance companies, actuaries usually calculate the death probability of an individual at certain age, before certain age, given that their age has already past certain limits. Like for example, what is the probability of a person dying before 50 years, given that his age is greater than 20? So what is the probability? So in this case, we use the conditional probability because there is a condition. His age should be greater than 20. And then what is the probability of him dying before 50? All right. Now, probability of A given B plus probability of A complement given B is always 1. Why? You can consider B as a sample space. So either A can occur or it does not occur. It cannot occur. Okay. And that will make up the sample space. That's why the probability is 1. All right. So this is about conditional probability. Now we need to understand independent events. Independent events. So these are few terms that we need to understand before we go into the depth of probability, because these terminologies will frequently occur in our discussion. So what is independent events? The occurrence of one event does not affect the occurrence of the other event. Occurrence of one event does not affect the occurrence of other event. Okay, so in this case, the probability of A intersection B equals to probability of A times probability of B, the product of the individual probabilities. Okay, Now, probability of A given B will also be the probability of A, the individual probability. Why? Because it does not matter whether the event B has occurred. These two are the independent, right? So this is simply the probability of event A, and you can prove this as well. There is a very simple proof. So what is probability of A given B? This is probability of A intersection B divided by probability of B, right? Now, since A and B are independents, you can separate the numerator, probability of A times probability of B divided by the probability of B. You can cancel this, and this is simply probability of A. All right. So from this, we can conclude that conditional and unconditional probabilities, conditional and unconditional probabilities will be same when events are independent. All right. Now let's do one last example and then we'll end this video. So suppose you toss a coin and roll a dice simultaneously at the same time. Okay. So what would be the sample space? The sample space is H can occur with either 1, 2, up to 6. Similarly, the tail can occur with 1, 2, up to 6, right? So this is the sample space. Now suppose the event A is getting head and event B is getting even number. So what is the set A? So A is head can occur with either 1, 2, up to 6. Up to 6. Similarly, event B is it says getting even number. So H comma 2, T comma 2, right? 2 can occur with either head or tail. Similarly, 4 can occur with either head or tail. And head can occur with 6, tail can occur with 6. So this is the sample, this is the event A and B. Now what is the probability of event A? So what are the favorable outcomes? So there are 6 favorable outcomes. You can count. There are 6. And what is the sample space? 12. So this is half. Now probability of B, again we have 6, 1, 2, 3, 4, 5, 6, and sample space is 12. This is half. Now what is A intersection B? A intersection B is the common in both A and B. So what are the common? H comma 2, H comma 4, and H comma 6, right? What is the probability of A intersection B? There are 3 favorable outcomes in intersection and sample space is 12. So this is 1 over 4. Now you can verify the independent rule A intersection B equals to probability of A times probability of B. What is A intersection B? This is 1 over 4. And what is the probability of A? This is half, and this is also half. So this is 1 over 4. So this is how you can verify the independent events. And one more thing, you can also um, you know, see that the tossing the coin and rolling a dice, these two are the different things, right? It doesn't matter whether you get the head or tail. It does, it will not affect the number that will appear on the dice. So these two are the independent events. So this, the relations should be verified. Okay. So now let's just stop this video. And in the next video, I'll go into the depth of the probabilities. I'll discuss the random variable. So thank you so much for watching this video.